We are on. So welcome everybody. I know it's a bit unusual for us to have these events on Wednesdays, but it was a very interesting opportune for us to do this, especially as we approach the start of the actual group theory section of the crash course. So far, we've been on, playing with toy stuff and stuff like semi groups, this type of stuff. But in the next session or the session after, we will definitely start diving into group theory. So the idea of inviting guests like Owen to give a talk on the application side of group theory is just to give you motivation, because you will go through a lot of boring stuff. So it's always very important, in my view, to have some sort of, break sessions. Sometimes invite people to motivate you, for you to see that the boring stuff that you learned actually is will be very handy in anything at a later stage for you. So today definitely is one of those talks, and I have 3 more talks at least scheduled. One will be on cryptography around the Diffie-Hellman key exchange protocol. Another one will be on geometric deep learning, and the final one will be on quantum computation, in particular quantum error correction. So plenty of motivation. So yeah. It's a pleasure to have our friend here, Owen. So Owen is a second-year PhD candidate studying topological full groups and continuous orbit equivalence under the supervision of Professor Lee at the University of Glasgow. He's interested in C-star algebras and their connections with the groupoids and topological dynamical systems. Just as a side note, C-star algebras is something that we will at some point. I know I promise people in the advanced members of the community, especially those coming from physics, that in the later stage, at some point in the future, we will do non-commutative geometry. But we will do that after functional analysis, and you definitely need to be aware of C-star algebras, in particular, in general, operator theory stuff before you are able to take anything closer to non-commutative geometry. So yeah, maybe Owen will actually be back to give us a talk on his research or something, or even maybe do some of the lectures on the thing on C-star algebras. Yeah, let's see. Owen, are you up to the challenge? I mean, are you willing to take the challenge?
Maybe, yeah.
Yeah, we'll see.
No, I think I definitely enjoy teaching a first course on non-commutative geometry. Can't lie.
Cool. Yeah. So just before I hand over to Owen, just a reminder: at the bottom of the bar, you will have like a question, ask a question button. Let me just put a test question so you can see it all pop up. Test question. So I really encourage you to ask the questions through the ask the question button, and please vote so that if we have so many questions, Owen can prioritize which one to focus on if you are running out of time. And I have our friend George too, who will be helping. And please feel free to ask questions. Really, this is one of the reasons that we are doing these side talks in parallel with the crash course. So feel free to engage with Owen, ask questions, and that's it. Enjoy the talk. I'm pretty sure you will enjoy it. So Owen, without further ado, I will hand over to you, and thank you again for taking your time to be with us.
Thank you for having me. It's very nice to talk to you. And yeah, I've been excited for this. So yeah, thank you. So yeah, it's nice to have this very nice introduction, but just maybe a little bit about me. So I did my undergrad in Cardiff. So I've been around the whole of the UK and stuff. And yeah, today I basically just wanted to speak to you as a PhD student, but also just to someone that's interested in group theory, a bit about the history of group theory and a little bit about some of the sort of maybe stranger applications coming out. So I'm glad to hear that you're going to get some really concrete applications towards computer science and coding, cryptography and stuff, because I don't know a whole lot about these. So I would probably butcher them if I was to talk about them. But I'm I'm glad that you're seeing them, because this is probably how you'll end up using group theory after you've learned a bit about it. But before that, I think it's good to have an understanding of why it developed so much as a mathematical field, and a little bit about how it finds itself in science as a whole. And so that's what this is all about. So the talk's not very long. The talk's about 20 or so minutes, because I didn't want to keep you guys after work. But I'll be around for the whole hour to sort of have conversations afterwards, because I figured that you guys are the audience, you know better than me what you're interested in talking about. So I'll get some ideas flowing, and then hopefully we can talk. Okay, with no further ado, let's go to my first three slides. So what's symmetry? So symmetry in school is kind of a bit of a trivial thing that we're sort of taught of in school, and it sort of goes away. It turns out that it's quite an important thing in mathematics. So in symmetry, we've probably learned a definition along the lines of you do something to a shape and it stays exactly as it used to be. And this did turn out to be pretty useful in school. I'm not like rubbing what it was in school. Like, for instance, we identified different types of triangles by their symmetry. So an equilateral triangle had these 3 lines of symmetries, an isosceles triangle had 1 line of symmetry, and also distinguish different shapes by their symmetries. However, when it came to high school, there wasn't much stuff on symmetry for most of us. And for most people in their degrees, there's not that much stuff about symmetry, whatever they study. But as you know now, what group theorists say, and mathematicians probably say as a whole, is that group theory is the study of symmetry. So it does turn out that this stuff is very important, and I'm going to talk to you a bit about why. So, but first of all, I'll talk to you a little bit about where group theory sort of came from. So the first people that were really studying symmetry in any sort of serious way would have been sort of Islamic scholars in the Ottoman Empire. So this is, I've put a date there around 825 Common Era, but this whole era is like an era of mathematical history that I think a lot of people could know more about. So, you know, this is where, for instance, Arabic number symbols were invented, where we first saw sort of like the plus sign, the minus sign, things like this. And this is like really where a lot of algebra comes from. You can hear that algebra is obviously quite an Islamic word, but this is the period where algebra starts. And yeah, I just wanted to give that a shout out because that's definitely the origin of group theory. And then sort of modern group theory is a little bit more European. So by the sort of mid-19th century, it was Galois who first wrote down the definition of groups, as you're about to learn. And people have done quite a lot with them since. So it's probably one of the few fields of mathematics that survived not only the change in foundation in the early 1900s towards set theory, but also the gradual change that we're seeing these days towards category theory. Everyone's sort of remained interested in groups throughout these huge cultural shifts in mathematics. And in particular, a question which has survived this was classifying all finite simple groups. So what you'll see is that these are like the periodic table of groups. These are like the building blocks of groups, which all other groups are made out of. And this is like a tremendous achievement of mathematics. It can't be overstated how much work went into this. It took over 100 years. It's definitely the theorem in the mathematics as a whole, which has the longest proof, if you like. And and it's said to, no one person understands the entire proof. It's different people understand different parts of the proof, type thing. So there's quite a lot that we know about groups these days. But there's all kinds of things that we don't know. I mean, in particular, we haven't classified infinite groups. And yeah, there's all kinds of other questions about groups, like can groups act on different spaces? Can groups have different geometric properties that still remain very open? So pure maths remains very inquisitive towards it. And I just got a few pictures to sort of represent a bit of the diversity of the field. So on the top right, we've got what a category theorist would probably be thinking about when they thought about groups, which is sort of like, this is the first isomorphism theorem in sort of a category theoretic language, which is nice when you get your head around the notation. You can tell it makes you really feel like you're doing some proper mathematics when you draw a diagram out like this. And then we've got a tesseract on the bottom right. So this is like an example of a 4-dimensional object. And yeah, this has a lot of interesting symmetries, but I thought I'd include it to say groups can be the symmetry of a 4-dimensional object as well as, a 3-dimensional or 2-dimensional. Groups get very strange in higher dimensions. We've also got this sort of Klein surface on the left-hand side, which is just like to say even 3-dimensional objects can have very strange symmetries. And yeah, what did I want to say about this? Okay, yeah, I also wanted to mention that so groups really are a generalization of symmetry, in the sense that every group every group is the automorphism group of some object. And what this means essentially is that every group is the group of symmetries for some object. And then on the flip side, all of these things are grouped. So there's this sort of equivalence between groups and the symmetries on an object. So why is it hard? Symmetry in primary school was easy, right? And now I'm telling you that mathematicians take hundreds of years to prove a theorem. And I'm just going to go ahead with even to tell you how complicated the finite case can be. So what I've got in front of me is a Rubik's Cube. Like everyone knows what these are right now. But something you might not know about a Rubik's Cube is that it describes a group, the Rubik's Cube group. So all of these things, these moves, which I do, can be thought of as symmetries. And if I, mess it up, that's a whole bunch of symmetries put together. So it forms the algebraic structure of a group. And that's a good example to think about when you do your group theory course. Now it's generated by 6 moves. I can do the left side, the right side, and then there's like the up, and then there's the down. And all of these, any sort of move that you do can be in terms of these moves. So you say it's generated by 6 moves. But over here, we've got a huge number, and that number is the number of different combinations you could have for a Rubik's Cube, and it's 43 trillion. And that's enough Rubik's Cube. If we had one for every combination, we would cover the Earth 275 times. So that's really like a big number, even from a professional mathematician. And yeah, what's the point of this? Well, the point of this is that the Rubik's Cube group has something called a God number of 20, which is if you got someone that was like a professional Rubik's Cube solver, they could look at this, and no matter how much I've, messed it around, they could solve it in just 20 moves. it only takes 20 moves to get to any one of these 43 trillion combinations. And this is essentially a lot of what makes groups useful, is that they have this sort of random-like quality where if you actually really get down and study the symmetries, you can often find them easy to solve. In particular, this is where it fits into cryptography, because the Rubik's Cube is a really good sort of canonical example of a problem which is easy to pose. It's easy to know when you have a solution that it's the right solution. It's easy to verify solutions. So if someone says this is the solution for the Rubik's Cube, then I would just do it and see if it's solved. Then if it is, then it's the solution. But it's very hard to just brute force it and work your way through all of the different solutions. So I'd say that this is a really good example to keep in mind, both for an arbitrary group, but also in terms of lock and key cryptography. I think actually there is like a historical note here about like the people that came up with this style of cryptography were really into Rubik's cubes, and it was like through this that they came up with this. Okay. Now the next thing that I wanted to talk about was just physics, basically, because this is really where I'd say a lot of the pure mathematicians that are interested in groups, especially very weird groups, like Lie groups or braid groups or these kinds of things, because there are all kinds of groups, believe you me. Otherwise, we would be out of job by now. Then, yeah, these have really found a home in theoretical physics in terms of their applications. So it's basically said that any conservation law has associated with it some kind of group. And, you know, in the Newtonian sense, this is really, you know, easy to see that these sort of things are in some way a symmetry of, say, like your two forces balance on a steady moving thing, and that can be thought of as some kind of symmetry. But when it comes to like really small objects, these symmetries can get really complicated. And the concrete example that I've got right here is Lie groups helping to simplify the Schrödinger equation. So the Schrödinger equation, as you may not have seen, is basically F equals ma for really small things. And it's pretty impossible to solve because you get tons of solutions. And one way to look at these solutions is to say, okay, well, I get all of these solutions. This appears to be the real simplification that lets you to really get information out of the Schrödinger equation. It's also used to look at very big objects, like in astrophysics, the orbits of different things, observe different symmetries that can get quite complicated. So this was an application that was like voiced to me quite recently. But yeah, I didn't have that on this slide yet. So there, yeah. But yeah, so this is sort of some stuff about physics, but definitely ask me a bit about this later, because I can talk a bit about symmetry in physics. It's very interesting to me. The next one that I wanted to talk about was in chemistry. So in chemistry, there's a process called NMR spectroscopy, which basically, given some sort of chemical solution, it gives you out what molecules are inside it. So you like put it in a machine, and then as if by magic, it tells you, okay, you've got this many of this molecule, this many of this molecule, like that kind of thing. And this sounds like an absolute wonder of science and like a magic machine. It turns out that this is really group theory is sort of what's going on here. So what the machine does is it will sort of vibrate all of these molecules and take note of their symmetries. And just in the way that in primary school you use symmetries to understand different types of triangles, NMR spectrometers use the symmetry of these molecules to understand what molecules they're looking at. And yeah, this of course has all kinds of applications. It's probably the most used sort of machine in most chemical labs. You know, you can test through what chemicals are in your medicines, what chemicals are in, I don't know, your bloodstream, like all of this kind of thing. Incredibly important for modern chemistry. The next one is viruses and symmetry. Well, I mean, we all know now that viruses are a lot more important than we want them to be. So it would be good if we could try and understand them. And one way as well to classify them is based upon symmetry. So it's important to classify viruses as well as something that we've kind of learned in the last few years, all of us. But I mean, people have been classifying viruses for ages. But to understand when, for example, coronavirus mutates into a new variant, when this is really something that's substantially different, substantially more transmissible, substantially longer half-life, these things can correspond to the symmetry. And the reason why is I'm talking here specifically about viruses like coronavirus that are of this form. So they have attachment proteins on the sort of main body, which look like sticky bits coming out of the sphere. So in order to understand these, we'll take a microscope image, but this is obviously a 2D image of a very 3D object. It can be quite hard to determine what shape it was, what virus it is. And the way which a lot of people can compute this is by looking at the symmetry of this shape. And this is actually the way that a lot of people would identify a virus and classify them, write about them in textbooks, this kind of thing. So that's a bit about how viruses and symmetry go hand in hand. Finally, I'd just like to say that studying group theory is pretty. Like, it's a really beautiful subject, and it's found all sorts of applications outside of science as well. So it's got an appreciation in art. I'm sure that everyone can understand where that comes from, but interestingly, it's used quite a lot in architecture. The way that humans have sort of like intuitive sort of designs about how a building should be comes down oftentimes to symmetry. In music, so the basis for sort of like anyone who can read music, the basis for this sort of notation and stuff can be written in terms of group theory. And yeah, I just wanted to also give this quote by Ian Stewart, who's a very prominent group theorist in the UK, that group theory is the study of beauty. So that some mathematicians even go this far to say that that's what group theory is. And then over here is a Penrose tiling, in case anyone's wondering what this pretty picture is. This is quite an interesting example of an object, actually, because it has no symmetry. Even though it looks very, very symmetrical, it only has sort of half symmetry, which is like basically groupoids rather than groups, which is what I worry myself over day in and day out. And that was basically it from my talk. But I definitely want to talk to people a bit about it. So I just wanted to give out a few further reading things. So this Ian Stewart book, Why Beauty is Truth, The History of Symmetry. This is a really, really great book to learn a bit about like the mathematical history of symmetry and just a bit of an appreciation for group theory in general. Then there's this Richard Lewis article. It's called An Enormous Theorem, the Classification of Finite Simple Groups. That talks about that huge theorem that I was telling you about, which is like, honestly, just, I mean, it's kind of strange that almost that no one knows about it because it's just taken so long and it's been so many people's effort and stuff. And then a final one, which I just think is a really like zen way to spend your time, is this book, Beautiful Symmetry, a coloring book about math. So it's like a regular coloring book, but basically all of the pictures have some like really nice application towards group theory. So you like learn a little bit about higher math whilst sort of coloring in. I just think it's really cool. And yeah, a couple of shameless plugs. So I've got my blog where I talk a bit about being a student and whatnot, and then a newspaper piece that I wrote, which is kind of like the newspaper piece version of this talk about symmetry. So yeah, how am I doing for time? 25 minutes on the dot. So has anyone got any questions? Because this is the part that I was most excited for about this presentation, to talk to you guys a bit about why you're interested in symmetry, maybe, as people working in tech. So I'm going to stop sharing, I think, so that I can see people. Hello.
There was a question if you can post the URLs, I guess, for people who didn't catch the QR code.
Oh, okay. Yes. So wait, I'll do that now. So my blog. And I'm also seeing some good maths questions that I'll think about on the what. So wait, this one and then my gist article. I'm seeing loads of interesting questions. Okay. So I think that's all my URLs, and I'll just start going through some of these questions in order. Okay, so first question here from Barry Bird. Is it really the case that category theory can replace set theory? Yes, it is the case that category theory can replace set theory. So so the people that were really big on set theory were like this group called Nicolas Bourbaki from France. I don't know if anyone's called this, but there's also a very famous mathematician called Alexander Grothendieck. He's like a bit of a mathematical hero to me, to be fair. Like, a really, really cool guy. And he was briefly in this sort of like Nicolas Bourbaki club that was trying to rewrite the whole of mathematics into set theory, and they did like foundations and stuff like this. And his idea was, let's not do this in terms of set theory, let's do this in terms of category theory. And that's basically what a lot of his research ended up being. But yeah, I'd say it's not happened in as much of a harsh way as the move towards set theory, but I really do believe that most mathematicians that work in pure maths would now say that the basis of mathematics is probably more category theory than set theory. Yeah, I think that culturally this is where we're heading. And then we've got a question here from Bob Miller. Can you give an example of a groupoid that has partial symmetry? So obviously I did give this example, but maybe I can give you a simple example. There's a few that I can give you actually. So there's actually a type of Rubik's Cube that has, groupoid structure. So I think so the simple example that everyone sort of gives is, this example of a 15 square. So it's the kind of thing that probably like you have seen, but then
Could I ask
yeah.
a quick clarification? We found that there's several different definitions of groupoids. So, which one are you using?
A category in which every morphism is invertible, but then also there's this generalization of a group definition, which is equivalent to this.
Okay, yeah, thank you.
Great. So this would be a good, easy example is a 15 puzzle. So this is like what a Rubik's Cube is to groups. A 15 puzzle is to groupoids. Like, this is like the example that everyone gives in their talk. So basically, you can see here that it's not a group, because if you move 7 down, you can only move 7, 10, and 11. But if you move 13 across, you could move only 13, 10, and 14. So in some way, you can only compose certain transformations. You can't compose every transformation. And this is like the key difference between a group and a groupoid, is that instead of having multiplication defined on everything, you only have it defined on sort of like a certain sequence of things. And that's what makes the 15 square like not a group, but a groupoid. Yeah. Another sort of more non-trivial example would be a transformation groupoid. This is the same thing as a discrete cross product, which you're more likely to come across in your thing, so, or like a group action. So this would be in like the Wikipedia page. Now, I'm really curious, this clarification question about, we found a whole bunch of definitions about groupoids. I'm curious whether you actually have, because I've only heard of one.
Some people refer to what's now called a magma as a groupoid, which is just a structure with the composition and nothing else, not even associative or unity or inverse.
Okay, yeah, this is like not what. Yeah.
So the magma word is taking over, but the other definition of groupoid still shows up.
I see. This makes sense. Okay. Yeah, so I never realized that this like a magma might be. Yeah.
And there is also an older definition of groupoids, which goes way back 100 years, and that I believe is more or less equivalent to the category theory.
Yeah, this is the algebraic definition. Yeah. Yeah. So yeah, this is just probably some mathematician from back in the day who called a magma a groupoid when they didn't realize that a groupoid was already a thing or something.
Yeah, it's one of those oddities that actually what's now the category theory definition is the old original one that's been brought back.
Yeah, 100%. So I got another question here. Oh, okay. In the class, you've also been using the magma definition for a groupoid. That makes sense. Okay. So I would argue in strong terms that it's a magma and not a groupoid. by most mathematicians' standards.
It's altogether confusing when you the terminology when you generalize a definition. So there's groups, semi-groups, quasi-groups, groupoids, and so forth. And I think people run out of prefixes and suffixes so that it's very inconsistent.
Definitely. Yeah. Hang on. So there's this other question. I've also heard that category theory can replace logic, but I'm not sure how anything can be more fundamental than logic. Don't category theorists use logic to prove things about categories? Yeah, I've never heard that, to be honest. And to me, I would agree with this argument. Like, nothing seems more fundamental than logic.
I think it's more of making a smaller world within logic, a kind of logic itself is very open-ended, and if you're not careful, you get paradoxes.
Yeah, I think that this would probably be the fair comment, is that category theory is probably broad enough to capture everything mathematical that we actually care about. And this is also definitely what I would argue with this set theory thing as well. Like, people say that there's certain examples of things. Yeah. No, I completely believe you. But it's not an opinion that I've ever heard.
Yeah,
I mean, people that are into category theory are usually into it in a big way. Like, they usually think that category theory holds the answer to all of their questions. But yeah.
Yeah, I mean, I think it's a bit like people got very super enthusiastic about, I'll call it Boolean logic, first and second order logic, and set theory, say 100 and more years ago. And both sides of that argued, well, logic is more fundamental or set theory is more fundamental. And they eventually slugged it out. But I myself, I question the idea that there is anything more fundamental than anything else, that you can turn the whole thing around. So I myself am getting interested in category theory, and it's beautiful and all. And so this idea of replacing everything that came before, I think, is a bit of a simplification.
Sure. I would tend to agree with this. I think the real thing about category theory is that it's very useful. It is useful when it comes to proving things. For example, my type of groupoids, there's a category equivalence between them and inverse semigroup. So you've got like this map, which takes groupoids to inverse semigroups and inverse semigroups to groupoids, which is called a functor, that you also get, that any map between groupoids maps into a map between inverse semigroups and stuff. And basically all of this is really nice because it means that everything that you know about inverse semigroups gives you something about groupoids, and everything about groupoids gives you something about inverse semigroup. And these kinds of things are abundant in mathematics and essentially can, it means that, you can do half the amount of work and prove much more things. So this is really a strength of category theory over set theory.
I would agree with that. That it's not so much like bricks and mortar, but the design for a mathematical object, and that it's a beautiful way of seeing connections between parts of mathematics that seem totally different. And
Yeah.
so you can
Definitely.
talk about those connections in a very structured way, and that's incredibly powerful.
Yeah, definitely. Yeah.
And so back to Barry's question, there is a kind of category called a topos, which kind of can be thought of as the category of certain kind of logic.
Oh, sorry, what was the question?
It was about whether category theory can replace logic when it uses logic. So it's, I'll oversimplify, but it gets back to the age-old problem of when you generalize too much, you can have paradoxes. This was a problem with set theory, which sets theory got around by saying that there is no set of all sets. That is too general an object. Because you can ask yourself, is the set of all sets a set in this sense? And you get into a rabbit hole you don't get out of. And I think that idea of a topos, and there's a similar thing in logic, the ancient paradox. The example is you define the barber as to be the person in town who shaves everybody that doesn't shave themselves. And then you've got a problem if you ask who shaves the barber. And so, again, I'm vastly oversimplifying. Something like topos theory is, another way to contain the wildness and say we're going to only allow these kind of questions.
Yeah. And I would say as well, there's still a place for set theory. I mean, I still see people that use results sometimes where, you might have the like diamond axiom or something like this coming into play. But, it's kind of quite a strange thing to do these days, to be honest. It's not as big as it used to be, I suppose. Yeah.
Even though there are still unsolved problems within set theory itself.
I think, yeah. I think it's fair to say that.
So just to kind of come back to Barry's question, my answer would be in a different way about fundamental of logic or set theory, and that category theory is a very powerful framework and in its way beautiful. I'm only just beginning to learn that, to talk about many, many areas of mathematics and the relationships between them.
Definitely.
Put it in line with this talk, it's kind of like a deep symmetry between different things.
Yeah, definitely. I mean, yeah. Yeah. Or just maybe like a symmetry in the way that mathematicians think about certain things.
Okay. Scrolling back, I don't see any more questions. But I just want to say thank you for the talk. I enjoyed it. And some very beautiful pictures of symmetry that you used. Those Islamic patterns are just stunning.
Yeah, they're great, right? Yeah.
I managed to find my thank you so much for driving all this, this discussion, George, and everyone else. Does anyone? I really want people to ask more questions, especially the thing. Ask advice on like especially those of you who are new on any questions about lessons and these things as for Owen that you would advise people study mathematics, for instance.
Okay, I've got one then. How do you use symmetry or math in your day-to-day work?
Yeah, I mean, actually, so like a lot of my research is about coming up with really weird examples of groups. So what I'm sort of aiming towards is to find examples of groups that are like counterexamples to von Neumann's conjecture, which says that if a group is non-amenable, it contains the free group on two generators. There are counterexamples in known, but I reckon I can get more. So basically, a lot of my research does touch group theory, and it's useful to think about it in terms of symmetries sometimes. So in my context, and the groups that I'm looking at are these topological full groups, which are the group of symmetries on a topological space, certain topological space, certain symmetry. So I'm simplifying here, but yeah, it's useful, and sometimes you can draw the shape, and sometimes you can really think about what these symmetries are. So yeah, it's definitely a useful thing for me, and I think this isn't true for just people that work in research. It's true for anyone that's studying maths at all. If you're working with groups and you can draw an object to really understand that group, you're gonna be onto a winner. Like, you have no possible way of understanding, say, the Rubik's Cube example, unless you had a Rubik's Cube in front of you, right? Someone just gave you this group in terms of like generator and algebraic relations. You'd be like, what the hell is this? But someone puts a Rubik's Cube in front of you, you can really understand it and get your hands on it. Yeah.
That's nice. I like the idea that there's also a playful aspect to math, that it's not just this dry definition, theorem, proof, lather, rinse, repeat, that you can have fun and play around with it. It's like a Rubik's Cube.
Yeah, definitely. Yeah, I like this idea as well. So we've got another question here. So do all symmetries define a group, and do all groups define a symmetry? Yeah, they do. I'm trying to remember what exactly.
We've got some noise from somebody.
This is okay. Don't worry.
Okay, it's probably me. Sorry for that. Yeah.
I'm just trying to remember exactly what the what this theorem is, but there is basically a theorem which says that for any group with a sufficiently nice class, you get a symmetry on a manifold.
I think to clarify Bob's question, that we kind of think of the symmetries as being something that we can see. So the technical term to connect these two, which we will be getting to, I hope, is a group action. So the group is kind of this very abstract algebraic thing sitting up there in algebraic Neverland, and this object that you can handle exists in a space or other less abstract thing, and the group action connects the two. So maybe what we think of as symmetry in ordinary terms is more like a group action than the abstract group.
Yeah, this is often a lot more tangible to understand a group. You can get all of its information from its actions. because in particular a group acts on itself, and this defines all of its structure.
Yes, that is actually something that wasn't explained clear to me years ago when I studied abstract algebra. They totally went with abstract, and it wasn't until much later that I got that aha moment.
Yeah, right.
Yeah, we will all be talking about all this stuff in the thing, especially when we move towards representation theory.
Rep theory is a really, really nice subject, definitely.
Does anyone has any other thing? Come on, advice. Especially the I won't say the no one is newbie. Everyone is like already. All of us. Any career advice and these things pursuing. Actually, a good thing to ask Owen is about how does he see himself on going forward, academia or industry versus have you decided or not yet?
Well, it's a hard decision. That's one thing that I definitely stress, is that academia is a great place to work, but a hard place to find work. That's what I'd say. I think what I've decided on is that for the next couple of years that I'm actually doing my PhD, I'm going to be very academia focused. Because 2 years is a good amount of time, right? Like, if I had a 2-year position in industry, I'd be very happy, basically. So I'm going to make the most of this, and then on the other end, I'll have to really think about this decision much harder. But I think I probably lean industry. That's what I'd say. I probably lean industry because amongst other things, I mean, I've got a long-term partner and I want to start a family and stuff like this, and it's very hard to do that alongside academia. Yeah.
So what you mentioned about amenable groups, is that related to your thesis topic?
Yes. I'm trying to find groups which are counterexamples to von Neumann's conjecture. So these are groups which are not amenable, but they don't contain F2. So they're weird in this respect. Most non-amenable groups contain F2.
Very cool. Good luck.
Thank you.
So I assume if you could pick an open problem that you would like, if you given the opportunity to pursue until you solve it, you would you pick, is it the von Neumann conjecture that you will go for, or there are others? There's another one that you would like if you could.
If I could solve any. So von Neumann's conjecture has been proven false. So I'll try and think of a few that there's a few that I think would be really nice in my field. One's the Baumann's conjecture. This relates the K-theory of groups C-star algebra to its K-homology. So this would be like a really deep connection between C-star algebras, which is something that I do, and group theory, which is also something that I do. But there's plenty of people that work with group theory that don't touch C-star algebras, and there's plenty of people that work C-star algebras that don't touch group theory. And I think this theorem, if it was, this conjecture, if it was proven true, it would really just be like, okay, we've got a B team together. So I think that would be a really cool one. And then perhaps more modernly, so there's my supervisor Shinli recently proved that every C-star algebra which is classifiable, which is like a really broad range of C-star algebras, is a twisted groupoid C-star algebra, and it's an open question whether every classifiable C-star algebra is a groupoid C-star algebra. I'd love to know the answer to that, but I don't mind if it's me that proves it or someone much cleverer than me. I just want to know the answer, you know. Yeah.
Couple years ago, I think I attended a seminar or something, or heard people discussing potential connection between C-star algebras and potentially the Riemann hypothesis stuff. Any comments on that?
I've not heard that there's connections there, but I can believe it. I mean, the Riemann hypothesis really is a gift that keeps on giving, because a lot of people just put a lot of work into developing theory. I mean, I think the Riemann hypothesis is a very hard problem, but what it's done is it's really broadened out from number theory out to all areas of other mathematics for people trying to find a proof. And so culturally, I think it's a really good thing for mathematics that it stays open.
Yeah.
Proving these amazingly useful theorems. And
that's so true. I mean, nobody really wants to dive back into Fermat's last theorem anymore.
Exactly. Yeah.
If you were to guess, had to think, would you? What's your gut feeling? Without, I know this is hard to ask a mathematician, because a mathematician doesn't like to go with gut feeling. You want to be able to prove something, prove it. Would you say, is it true? Likely to be true? The Riemann hypothesis.
The Riemann. I think it's actually maybe even likely to be unprovable. This would be the really hot take, because I mean, people.
Do you mean
people have said this? It could be the first, like.
Do you mean like undecidable in the sense that it could go either way from within arithmetic? That would be amazing.
Yeah, I'd love to see that. Yeah, because there's this whole bunch of maths that's like assuming the Riemann hypothesis true. I mean, obviously everyone, like most people would think that it's true. But I think that, well, it's known that it's logically consistent to assume that it's true. So that wouldn't like break anything, but it's not known if it's logically consistent for it to be untrue. But in that sense, if it was proven to be logically consistent for it to be untrue, then that means it's unprovable.
I think this thing I was mentioning about C-star algebras and Riemann hypothesis, I think it was something related to this thing that Alan Kohn wrote in this essay on Riemann hypothesis.
Yes.
I'll pass the URL.
Do you know what? Yeah, I think there he is. He's going for it. Yeah. I've heard this. Yeah, he's going for it. He's going for the Riemann hypothesis. I think.
Yeah.
Yeah, I mean, if anyone can do it, it's probably him. Like he's really had. Yeah.
For those of you who probably, I think most of you probably not heard about Alan Kohn. I think, is he one of the co-founders or the founder of non-commutative geometry? How would we credit it?
Yeah. I'd say he founded it. He founded the program. Okay. Maybe with refill, but yeah, he kind of founded the program. And yeah, and he's Kohn from the Baum-Kohn conjecture that I said was the open problem I'd really like to see proven true. Yeah. I don't know. Yeah, he's a bit of a legend. He was part of Bourbaki as well. So he's part of the bunch of people that rewrote the whole of mathematics into set theory.
Oh yeah, in this case, wasn't he a bit? I heard that he had a bit of clash with some of the Bourbaki members. I think he left.
Yeah, I think everyone did.
One of them.
I think they were difficult people.
having, the French style. Huh?
Yeah, I mean, they were also famously quite sexist.
Yeah.
This was a lot of people's problem with them. Like,
Many
And
times, yeah.
as a geometer, they left out a lot of mathematics. So they did a ton of algebra and set theory, but huge realms of mathematics did not fit into the Bourbaki program.
yeah, right. This is true as well. I mean, another big problem.
That kind of touches that I was hinting about foundations. So really, not all of mathematics could be done the Bourbaki way. So maybe it wasn't that fundamental, even though it was wonderful in what it did accomplish.
Yeah, I think that would be maybe a fair thing to say.
It's very interesting. And also another thing, part of it, isn't it, that the members have to resign after they reach 40 something. So they only wanted like young. I think before 50, something like that.
This is
Yeah. That's another of the myths, that you have to be this brilliant teenager and then it's all over. Coming from Galois, of
I'm not
course.
sure, I think.
But,
I wasn't sure.
But Grothendieck kind of showed them wrong. He did more amazing stuff after he left them.
Yeah, later ages, yeah.
Yeah.
And does anyone have any other questions? And I have a question about education in math, since this community whole thing was is started about exposing these abstract structures to people coming from STEM background, but not necessarily to like mathematics, but like computer science and other. How do you think, in your experience, Owen, being exposed to mathematics at high school level, do you think the mathematics, the way it's taught at the school level, prepares the students enough for them to appreciate or not have like struggle to the university level stuff?
Yeah. I think it's a really good question. Yeah, what I would say is I think that it's hard to write a math syllabus. Like, I'm not jealous of the people that do this. I'd say that in high school, there's probably some debate to be had. But what I would say is that primary school mathematics, the way it is on our syllabus, I think is absolutely spot on. I think people really get taught the fundamentals that they really need to be taught in primary school, that gives them good intuition for university level maths. And that's the part which I care about the most, because that's where people are really developing their minds. So I think in that way it's a good thing.
I couldn't agree more. I think children are natural geniuses, and that if you're not careful, school dumbs them down for life.
Yeah. And I think our schools do an okay job. Maybe not perfect, but an okay job with primary school kids.
Well, that's really good news.
Yeah. I've just realized the time, and I need to be heading off in a sec. So
Yeah. So, well, no, I don't see any other questions, George. I don't know if you see any questions that's pending, but I think we can leave it here. And thank you so much again, Owen, for taking your time for this insightful talk. I hope the community members, I'm pretty sure they did enjoy the talk. And we'll hope to have you back again, especially in the advanced stuff when we go through functional analysis stuff. Definitely a non-commutative geometry stuff. You we hope to have you back. For the time being, thank you so much again, and have a good day. And George,
great.
Thank you so much for moderating. And everyone, I see you on Friday.
Okay, thank you very much. Bye-bye.
Thank you all. Thank you. I'll follow up with you on the email. Cheers.
Cheers. Bye-bye.